Okay, hello all and welcome to our third IBIPSA seminar for the year. My name is Rokia Raslan and I will be chairing this webinar, which revolves around the use of co-simulation for advanced building performance assessment. So co-simulation allows modelers to use multiple submodels and link them to enable simultaneous data exchange during simulation runtimes. It provides added possibilities for implementing such things as advanced control strategies, integrating innovative data-driven input, and creating collaborative, interdisciplinary, and evolutive workflows for building envelopes at different stages of designs and scales and projects. And today we've got two very fantastic presenters who will be discussing some of the latest knowledge and development regarding the use of co-simulation in two areas. Firstly, Dr. Esther Barkowski, who's a postdoctoral researcher at ETH Zurich, will discuss how co-simulation was used to develop an integrated approach to modeling control strategies for adaptive building envelopes. And then very happy to also have Dr. Giulio Vita on board, and who is a senior wind engineer at Worth Research Limited. And he'll take us through its use in assessing airborne infection risk inside buildings. So I will revert to my first presenter, Esther.
Hi.
We'll start the presentation.
Yeah, thank you, Rokia. And yeah, good afternoon, everybody. Let me quickly share my screen.
Apologies, before Esther starts, we would welcome questions from the audience. So if you do have a question, please do post it in the Q&A section of the chat, which can be found at the bottom. Towards the end, I'll be fielding your questions to both of our presenters and getting their feedback. So please do post them throughout the presentations. Thank you, Esther.
No worries. So yeah, again, good afternoon, everybody. I'm really happy to be here. And before I started my postdoc here at ETH 2 months ago, I did my PhD at UCL. And today I'm sharing part of the work I did during my PhD with you. So let us jump straight into it by looking at the difference between traditional and adaptive building envelopes. Traditional building envelopes, they're only dynamic to a certain extent, only when a user starts to interact with the facade and, for example, opens a window or closes a blind. By contrast, additional building envelopes can dynamically adjust some of their behavior over time to changing environmental conditions without necessarily requiring a user input. And that dynamic behavior of adaptive building envelopes is achieved either through the dynamics of the building envelope itself, as in the case of phase change materials, or through mechanical actuation through a control system. And the main problem in design practice and beyond is that current building performance simulation tools are limited in predicting the performance of control strategies for adaptive building envelopes. And there are many, many reasons for that. Some of them are listed here. And one of the main limitations is that it's challenging to adapt the tools to new models and functionalities, as the solvers can be poorly integrated with the existing solvers. And this limits the possibility to develop models for specific adaptive building envelope technologies, especially emerging ones. Another limitation is that current building performance simulation tools cannot perform structured design space explorations, as they cannot solve non-convex optimization problems with continuous and discrete parameters. And these optimization algorithms are rarely integrated. There are, of course, a few exceptions, like Design Builder, for example. And because of the limitations of current building performance simulation tools, part of the aim of my PhD was to investigate how to accurately predict the thermal performance of control strategies for adaptive building envelopes. And I used several methods to achieve this aim. The first one was that I conducted interviews with industry representatives to improve the understanding of the limitations of simulating adaptive building envelopes in current design practice. And based on the findings, I then developed a potential approach for the integrated modeling of control and adaptive building envelope to predict thermal building performance. I then went on and validated the modeling approach using empirical data from MATLAB, a test cell at the University of Cambridge, to investigate occupant facade interactions. And finally, I tested the functionality of the modeling approach through a case study. Today, I will mainly focus on the modeling approach and a case study I did during my PhD in collaboration with Arup. And since the development of the modeling approach was based on the findings from the interviews, let us quickly look at the results. So I found that current building performance simulation tools hinder the reliable prediction of the performance of adaptive building envelopes. And this is because the accurate representation of the level of detail of adaptive building envelopes is perceived as challenging. The workarounds applied in response to these limitations are either time or cost intensive, or do not take into account the dynamic components of the building envelope. And as a consequence, more flexible modeling approaches that allow for rapid prototyping and easy integration of tools and functionalities are needed to allow designers to take full advantage of adaptive building envelopes. The interviews also highlighted that practitioners need to address complex issues at the control, building envelope, and even the whole building level to answer questions related to the performance of adaptive building envelopes. And this is why the modeling of adaptive building envelopes requires the predictions of the interaction of multiple components and technologies. And this in turn requires the development of models that allow these components to be linked. Two common methods of combining models to simulate whole systems are either standalone simulation, also called monosimulation, and co-simulation. In monosimulation, a system is represented by one model that is executed in a dedicated simulator, and this method is used in most of the building performance simulation tools that we use. Co-simulation, on the other hand, refers to the joint simulation of separate models developed in different tools. The models are run in individual simulators, and they can work together. While the tools communicate with each other at specific times and synchronize outputs such as variables or status information, each tool independently solves one part of the coupled problem between these communication points. So the modeling approach that I developed in my PhD makes use of co-simulation and couples Energy Plus for the thermal simulations with Daimler for the control simulations via a co-simulation interface. And the co-simulation interface that I use was the functional mockup interface, short for FMI, standard. And this integrated model was then wrapped with an optimizer to understand controller parameters and to indirectly select control strategies for the building envelope. And to automate and manage the entire workflow, I used Python, and I also used Python to incorporate the optimizer and a coupling function to communicate between the optimizer and the co-simulation model. In the case study that I present to you today, I used the modeling approach to optimize controller parameters for an adaptive building envelope. And that could be, for example, important for design practice to overcome the trial and error difficulties that are typically associated with standalone simulations. As a case study, I chose an 18 square meter bay of a typical floor of an office development in central London. The south-oriented facade of the case study was a closed cavity facade with an automated motorized blind. The blind in the study had 6 different positions, from open and then horizontal, various tilted to closed. And I investigated 2 control strategies. The first one, C1, was a rule-based control strategy that I used as a baseline. And in this strategy, the blind positions were based on solar gains to minimize solar heat gains and on sun tracking to prevent glare. In the second control strategy, C2, the optimizer indirectly selected the controller parameters for the blind. And the optimizer used a multi-objective optimization approach that aimed to minimize the energy use on the one hand side and indoor thermal discomfort on the other hand. As I said before, the control simulations were run in Dymoller, and here you can see the controller model that I developed in Dymoller. I created the model so that I could use the same model for both control strategies, and I did this by adding conditional clauses to the blind position y blind and the slat angle y slat in Dymoller, so that they were mutually exclusive from the components of the baseline model. And in this way, the optimization simply overrode the blind with a set of controller parameters that were obtained by the optimization algorithm. I run the simulations then for a typical 3-day summer period. And as you can see here, the control strategies, both control strategies significantly influenced the positions of the blind. This graph shows the percentage of time the blinds were open or tilted or closed or whatever during occupied hours. And while the blind was open almost half of the time during occupied hours in C1, which is the dotted line, it was never open in C2. And even when the blind was shut down in C1, it was less often in tilted or closed position compared to C2. The different way the blind was controlled also affected the performance of the case study, because the blind was more often in tilted or closed position in in C2, less heat entered the blind through the building envelope. And so the window heat gains in C2 were significantly lower than in C1, especially during the day when the blind was active. Oops, sorry. And as the window heat gains were lower in C2 than in C1, it was not surprising that the energy consumption for space cooling was also lower in C2 than in C1. And these differences, they can be explained by the objective function, which was best able to minimize the energy consumption when the blind was in tilted or closed positions. But since there was no direct sunlight passing through the building envelope in the case of C2, it could be assumed that the energy consumption for artificial lighting was increased compared to the baseline. On the other hand, it could also be assumed that the risk of glare was decreased, which might have improved visual comfort. And since the optimization successfully reduced the energy consumption of the case study, it could also be concluded that the findings are suggestive of the benefits of adjusting the dynamic aspects of the building. And this in turn suggests that co-simulation offers benefits for the simulation of adaptive building envelopes. And although co-simulation has many benefits, there is still some open challenges that need to be addressed in the future. For instance, there is a lack of a systematic standard approach for performing co-simulations, which is supported by the fact that there is no one-size-fits-all solution to co-simulation. This usually leads to customized solutions for the specific applications and tools used, which could make co-simulation more difficult to use in practice, but could also contribute to the limited awareness of the potential value of using co-simulation is the lack of widely available recommendations or guidelines on how to approach co-simulation tasks and how to overcome the technical challenges of implementing co-simulation. So there's still a lot of work to be done until co-simulation hopefully one day becomes standard practice. So this brings me to the end of my presentation, and I hand it over back to you, Rokia.
Thank you very much, Esther. It was really interesting to see how it's been applied to the area of adaptive facades. And I'm sure, like myself, the attendees will have a lot of questions, which we'll be discussing towards the end. Our second presenter, as I mentioned, is Giulio Vita, and he'll be talking about the use of co-simulation assessing airborne infection risk indoors using dynamic thermal modeling and CFD. So, Giulio, if you would like to start your presentation.
Yes. Right. Thank you, Esther, for a very focused presentation. What I'm going to talk about today, can everybody hear me? Yes, should be. What I'm going to talk about today is our early experience on assessing indoor airborne infection risk using DTM, which is dynamic thermal modeling, and computational fluid dynamics. We will give our perspective, and we will give some food for thought on a general view of the problem and how it can be dealt with in practice. So this is the outline of the presentation. I will give the motivation, why we are asked to investigate airborne infection risk in buildings. I'm going to present the co-simulation framework that we came up with, giving a bit of introduction on ventilation and airborne infection risk. And then I'm going to present two test cases that have been successful, recent test cases that we have worked on. Basically, the public is asking us to deal with airborne infection risk due to the pandemic of COVID-19. Although this presentation is not directly related for COVID, the public is asking to have better buildings. How the pandemic has been managed is by asking people to do something, so to wear a mask, to go get a vaccine. But actually, what we could be doing is to provide passive protection, so you enter a building as such you are protected against getting contagious. There is some guidance on how buildings can help us reduce the risk of contagion. Those involve mainly opening windows, increasing the filtering of air, or increasing the fresh air intake. Unfortunately, what we think is little information exists on how effective those methods are. They also interfere with comfort, which is a very dangerous field. To reduce comfort, to do something that is not clear how effective it is. So we think that we already have the tools to actually provide some more guidance to improve knowledge and ventilation. Among the different methods to assess ventilation, there are different levels and different things. Actually, these three methods, they kind of do the same thing, but they also do very different things. First, we have analytical methods. They are based on assuming constant parameters for your room, normally a single room, and they are extremely well known in the industry. They're used to have an idea of the general early risk level of your design. Dynamic thermal modeling is also very well known and implemented when designing buildings. It is, unlike analytical models, it is a complex model, so it allows you to do multi-zones, transient behavior, and allows you to include the source and sink terms in a way that is basically very free and very flexible. What you end up with is having a zonal dilution ratio. So instead of having one single dilution ratio for a single place, you have multiple ones for multiple zones, and all heat transfer modes calculated. The CFD is, if you want the most complex one, it allows you to model all geometric features and obtain a local dilution ratio. So you can actually see within the same room how your local dilution ratio varies. Before dealing with the differences and why we are using one or the other, or we use them together, why do we need to do CFD for a building? That's normally not something we would undertake to design a simple building. Well, flow pattern identification normally is absolutely useful to both practitioners and the building managers. So decisions are taken based normally when CFD results are taken as a result of having CFD results. They're useful to verify assumptions that you're taking in your simple analysis, such as DTM. And in general, they allow you to have better performance of your end object. This is a major switch when CFD comes into place from a compliance-based design, so respecting some standards, to performance-based design, so verifying that my design performs. We might say actually that when you have cases of natural ventilations or exhaust plumes to investigate, or even an interaction with indoor and outdoor, CFD becomes a game changer. So sometimes we feel CFD is needed. If we look at the limitations of all the free tools that we have seen, we see that analytical methods are the most simple, but as such, they are the fastest. So they are absolutely important when you're designing a new building. And what they, however, are based in is heavy assumptions, such as the well-mixed condition, such as the constant dilution rate in a room. So in a single room around the single source, the dilution is the same everywhere. DTM and CFD, of course, don't have this limitation, but they have their own limitations, although being complex methods. DTM is a unsteady method, so it allows you to have results varying over time. CFD normally doesn't, unless you're doing some specific applications. In industry, we do steady CFD mostly. As regards the physics, the DTM allows you to solve all heat transfer modes, particularly radiative and conductive modes are calculated directly, whereas in CFD, we do have models to consider those, but normally we don't consider radiative and conductive heat. Convective heat is directly calculated in CFD, whereas in the DTM is simplified because you're assuming the velocity field being constant within your zone. Even zones are a simplification of the reality because there is a single point representing data for a whole volume, whereas in CFD you have the actual variation of the volume. And then what's really the biggest limitation of both methods is the validation. Normally, we don't have a strong validation that says that basically our calculations are correct. In the DTM case, however, there is a huge experience on using this method. In the CFD, there isn't. What you can draw is a parallel. So actually, the limitations of CFD are the strength of the other method. And this is true. They can be complementary. Sorry, they're knocking at my door. I'm so sorry. Well, it's working from home problems, I suppose. So how complex is to set up a DTM simulation compared to a CFD simulations? Where our opinion is that there is a comparable effort in setting those up. The complexity of the DTM comes from the huge number of parameters that you have to input in your simulations. Those parameters are a bit less in the CFD. Still complex, the CFD though, because you need to discretize your model and divide it into cells so that you describe the flow features correctly. Then you define the sink and source terms that drive your thermal behavior in the DTM. In the CFD, this step is normally the fastest one, but still you need to assume that your assumptions are correct. The solution step is very fast in DTM, whereas in the CFD can be quite long days to achieve a solution, but normally all that is required is for the individual to wait for the solution. They are insisting knocking at the door. I'm so sorry. That's nothing I can do. In terms of output, the CFD is more immediate. It's a steady simulation after all, whereas in DTM, you end up having a large amount of data that you need to analyze. So we would say that it takes a comparable effort to set those up. It is, however, very important to make the two tools collaborate. And we came up with this co-simulation framework where first we simulate the DTM. We have a transient solution where critical conditions are understood. We take those critical conditions. What I mean by taking is surface temperatures and results to inform our CFD. So we model the CFD in a way that the surfaces are defined in a similar way as the DTM, and they are then informed by the DTM, so the boundary conditions reflect the results of the DTM. We can also use DTM results to verify the CFD solution, meaning that the CO2 concentrations, for example, can be a great way of making sure that both simulations tell the same story. And then we come up with an airborne infection risk methodology to estimate the infection risk, which is relative for your building. That's the way we formulated it. The performance-based design of the building, of the ventilation system can then take place. We can focus on comfort, we can focus on air supply, we can focus on the layout optimization, so moving grills around or moving tables. This can be extremely useful, especially for facility managers. We can reduce the use of energy. This is actually the most important part, because in the climate change era that we live, reducing the ventilation that you need by increasing the level of testing can be extremely interesting. And there is a last part that is basically responding to clients' requests. And this can be a very, very tricky part because sometimes clients come up with all sorts of things. If we want to give a methodology to estimate risk, what we did is we went to the literature. We took a methodology that is broadly accepted, but you have to also to understand that it's extremely debated at the moment, airborne infection risk in literature. So none of the methodologies basically are they're still knocking on my door, by the way. I'm sorry if I get distracted. It's really distracting. Basically the methodologies are still debated. So there is a scientific debate. So we basically don't really know how to model properly and accurately airborne infection risk because there are some assumptions. So what we did is basically mutuated that into our calculations. We insert the infectious people as mannequins, so we model them in a simplified way. There is an inlet that simulates the mouth and the exhaled breath. The large assumption here is to assume that the volume of exhaled air is assimilable to a number of particles that compose the aerosol in which viruses are transmitted. We then know how many cubic meters of respiratory fluids are spread into a volume. And then we're able to calculate the dilution ratio from the CFD results. If we assume a viral load, so we assume that for a given volume of respiratory fluid, there is a number of RNA copies and an exposure time that we normally fix at 1 hour, we calculate the inhaled airborne infection rate. So the inhaled is basically the dilution ratio at all positions, which potentially might affect the susceptible people to become infected. What we use as a way of interpreting what happens to be a number is a human infectious dose. This is the bit that is most debated in literature. So some people say we shouldn't be using quanta. Some people still talk about probability of infection, but this is basically a mathematical term that seems to have little to do with the nature of how viruses are spread, because we don't really know how to measure them properly when they're airborne. But nevertheless, we're using this because it's quite easy to understand. So how many inhaled copies are comparable to what's considered a dangerous or a significant dose? If we go to our test cases, this is the office that we have modeled. It's an office in central London. It's mostly open space. There are 350 occupants in here, and basically there is a 350 occupants. 16 of those are infected, and we are placing infected people not based on some probabilities of a person being infected, but of a way of stress testing our system. So we are placing people in places that either from the DTM or from what the client told us, we might find it useful to see how airborne infection performs. There is the CO2. As you can see, there are CO2 concentrations in this graph. basically, those are the outcome of the DTM simulations, and we use them to identify what is the highest concentration of the day, and this would constitute the CFD boundary conditions. So we take all the surface temperatures at that instant of time to set up our CFD. The CFD results basically give out velocities, local velocities varying. As you can see, this velocity field, the velocities are pretty much uniform. This is very common for well-ventilated places. There are no seeable differences within a environment. What we see is that there are some places where the velocity is more streamlined, so more laminar, more faster. What we can see also is another parameter, that is the mean age of air. The age of air is basically the solution of the transport equation and measures how old the air is from the fresh source to the to any location in your domain. And as you can see, both of them, they don't really tell the same story. So what is considered good in terms of velocity, which is basically all the places that are inhabited, is not really represented by a place where all the age of air has some uniform characteristics. And this is kind of the same with the dilution ratio. The dilution ratio is basically very different with very similar air conditions. This is extremely interesting because it means that the dilution ratio is not immediately explainable with the airspeed, but we know that if we affect the flow pattern, so if we modify the flow pattern, we're able to modify the dilution ratio. What we did, we calculated CO2 concentrations and then compared with the early airborne infection rate that I explained earlier. What we see is that this is also a hot topic currently, if we can use CO2 concentrations to understand the liability to risk. So basically how risky an area is to contagion based on CO2 concentrations. If we look at this office here, being occupied by a single person and being a large office, the CO2 concentration is very low. Whereas the early airborne infection risk, if that person is infecting, can reach high values. So of course the CO2 is modeled for all the occupants, but it might not be enough to understand how the behavior of a room is. This for us is a very important result that we must say our client took really, they were really happy to see this, and they actioned something following this picture, because for instance, this is a meeting room, so they started placing the table in a different way, etc. Another test case which is of interest, I'm trying to be as fast as I can, is an existing industrial bakery. Being existing, the problem is that normally there is a lack of data associated to it. So in this case, we didn't perform dynamic thermal modeling. What we did instead was we went in there and measured the surface temperatures using IR methodology. What we have is a very large storage warehouse, which is fitted with ovens. These ovens are basically grills open to the air. They do pancakes, they do all sorts of things at industrial level. We didn't even know what the ovens, how much heat they gave at points, so we needed to model them in CFD2. In this way, using IR pictures and model our own models, we were able to set up the CFD with appropriate boundary conditions. If you remember the previous slide about the office, you can see that, for instance, the age of air shows very different numbers. So before we were speaking about an age of air of, if I can go back, around a minute. So this is around a minute inside the building. What we see here is an age of air that goes up to an hour and a half. So this parameter is actually quite important because it's a great way to showing where the problems occur, because it's very, very easily disturbed, let's say. The way I modeled this building is including openings in these 3 sides, which were not ventilated, and fully ventilating the area we were interested in. And as you can see, you can immediately see the difference in the ventilation performance. This graph from the velocity is about comfort. You can see that even the comfort is quite positive, but still there are some areas where the velocity field is quite different. So in this case, the well-mixed conditions probably do not hold because you have very different airspeeds within the same room. If you look at the dilution ratio, it basically tells a similar story as the edge over. So you have a very well-ventilated room associated with a very poorly ventilated room. The way we inserted infectious people in this case was slightly different because we modeled all of the workers at the workstation, and instead of modeling a mannequin, we just modeled the sphere suspended in air, not to disrupt the flow field. And what we did in this case is we stress testing the system, as I did for the previous one, but we also started playing with the viral characteristic to the viral parameters to see what happens. And basically what we can conclude is that first, changing the viral loads has a massive impact on the poorly ventilated areas, whereas it has little effect on the ventilated places, which is an extremely important result because it basically says how resilient your system is to the random nature of a contagion, of a contamination. The effect of the viral load is very similar also to the effect of changing how many particles there are in an aerosol, which means basically a different activity performed. So in this way, you can easily show to your client how well the system performs in extreme conditions. And if I zoom in for a moment, we can also see that in the well-ventilated area, there is still a 12-meter aerosol transport due to the local natures of the wind. So we can see that this source, for instance, remains pretty much within the 2-meter radius, whereas this one is spread for 12 meters. So this is quite important. If we want to conclude, we can say that the experience so far has been positive with modeling airborne infection risk, meaning that the clients normally are very responsive and give positive feedback. We can also say that there are still lots of uses for CFD, can provide guidance to designers, can provide guidance to architects, can provide guidance to facility managers. The methodology needs to be improved. So for instance, we should start talking about relative risk rather than modeling a physical parameter. But what we can say with quite enough confidence is that in poorly ventilated spaces, increasing ventilation does have a positive effect. Whereas if you already have a good, well-ventilated space, increasing ventilation or dilution might not probably be the solution because the system is pretty much insensitive to changes in viral loads and activities. For any extra information, I leave you with this link. And if you have any detailed question, you can always either ask me now or email me. Thank you.
Thank you very much, Giulio. And many thanks for taking the time to present this with so many people knocking at your door today. Perfectly timed as usual. We've got a few questions from the audience so far. So I'll start with the order that I've received them. The first is directed at Esther from Andrew Williamson. And Andrew's asking, as part of the process, do you have a baseline condition based on a real building that has adequate energy metering and monitoring of the various MEP systems to enable you to take into account system and building lag response?
Yeah, thanks for the question. I'm afraid, unfortunately, no. So the case study that I've presented, that was a building that was still in the design phase. So we had no metadata. So what we did was, as I said in the presentation, that was a collaboration with Arup. And what we did was to compare the result of the co-simulation with the model from Arup, but that was all we did, and no metadata unfortunately.
Thank you very much, Esther, for that. And Andrew, we hope that this highlighted or answered your question. The next question we've received in the chat is from Manoj Kumar, and it's directed at both of you. And his question revolves around what are the challenges you've come across in the co-simulation process? And are there any recommendations or advice that you can give to new researchers who are thinking of using it? So shall we start with Giulio first on this one?
So our experience is on CFD particularly is that people tend not to trust whatever comes out of the software. So a question we receive very often is, how do you validate your model? In my opinion, this is solved immediately if you have two very different simulations that tell the same story. There is very little margin for interpretation. So this could be a solution to what Michael has raised, that people with different skills start collaborating a little bit more. There is also a real difficulty in the modeling aspect of things. So for instance, if we take DTM and CFD, normally we have we allow for some resources to the modeling. So if we have to do the model twice, especially if we need to modify what we would normally model in a different way to be informed by the other model, this could be significant to our revenue and the doability of things. So even the time, sometimes we're asked for results in a week. So this is a real challenge in practical terms. And then there is another challenge, which I would pose to academics, is that the conditions that we are modeling, so they need to be generalized. So normally in academia, you model an experiment so the conclusions can be extrapolated a bit, but not really from a single piece of research. Instead, we need to be as general as possible because in the end, we're asking people to spend their money to have our results. So ways of generalizing the amount of work that you do and how relevant they are, that's a real challenge that, in my opinion, should be discussed more.
Thank you so much, Giulio, for that. And Esther, from your perspective, and being within the research field, what reflections would you have in terms of the challenges in co-simulation, and for anyone looking to include them from a research perspective into their work?
Yeah, I think for me, there were two levels of challenges, I would say. The first one was to couple the two tools, or whatever amount of tools you use, but to couple the tools with each other. That was actually pretty straightforward also, because there was lots of information. But then coupling or integrating Python into that whole workflow, that was much more complicated. And then to link that to the optimizer. But that's probably another story. But there are lots of resources out there, lots of people using co-simulation. So I'm really glad that in the community there were so many people happy to help. And I would really recommend to use that knowledge in the community.
Thank you, Esther. Which takes us to our next question from Michael Robertson. So Michael has mentioned that there is a real skills gap in industry for building physicists who have coding and data science skills, as well as having the accreditation recognition required. He rightly mentions that it is essential in his opinion to integrate co-simulation into standard working practice. And I noted both of you either worked with industry or within industries in co-simulation. And outside those, he has mentioned that there are rarer bespoke assessments that are requested by clients who are more forward thinking. Would you, each of you, kind of have any ideas on how you would tackle this issue? And Giulio's already touched on it, so I'll start by speaking to Esther. How can we get industry more on board with integrating co-simulation into their practices?
Yeah, that's an interesting question. When I collaborated with Arab during my PhD, the facade team particularly, yeah, they told me that it's a bit difficult just for them to implement such tools. They haven't been used before, and they were also talking about dye-moller, which is not used in the facade industry so much. So I think probably from a research perspective, more collaborations between research and industry would probably help. I said to let people know about how they can overcome the problems they're facing, because now in the facade industry, there are problems and difficulties with modeling the dynamic components of adaptive building envelopes or other dynamic components. So just talking about the problems and then finding solutions, because there are solutions to most of the modeling problems people are facing.
Thank you, Esther. And Julia, you've already touched on this, but do you have any other thoughts on how would we tackle this issue, given that you are working in industry?
Sorry, I'm struggling finding buttons. I think, yes, I would stick to my previous point that we should collaborate more. And in this regards, even I'm addressing Manoj's question about recommendation advice to the new researchers. I think what we should do as a community of building physicists or building performance simulators should be collaborate with academia. So that should be something that we do more and more, the collaboration between industry and academia. And for instance, Esther would have more baselines to, even in research is a big problem to find data, whereas for us, not really, so we can easily provide any data. So yes, this I think is key.
Well, I'll take that as an invitation to approach industry more within this line of work. We have a question from an anonymous attendee, so apologies, your name hasn't turned up. And this one is directed to Giulio. So from what you've seen so far in your results, can you conclude that the mean age of air, or another domain variable, is a better predictor of viral load/infection risk than using CO2? And I think you've already touched on this.
Yes, I think this is very clear from not only what I've shown, but other jobs that we have been doing. So this is normally the problem with the age of air. Unlike the CO2, the age of air is something that requires, it's basically a small CFD simulations. You need to solve the transport equation. There's no workaround, or you need to go in there and measure. So it can be only done in CFD, but absolutely much better idea of how effective your ventilation system is than the CO2 concentration. I agree.
Thank you, Giulio. And we have so far a final question from Majid that's made up of 3 parts. The first is, how is the dilution ratio defined?
Mm-hmm. So the dilution ratio is basically the percentage of volume that comes out from the source that is delivered to any position of your domain. So it's a percentage. It's a ratio between the source and the susceptible position. Yes. So it's.
Okay. And the second part of Majid's question is about droplet simulation. So he mentioned that it was said to be with multi-phase modeling with diffusion. And he asks if you considered evaporation.
Well, the problem with CFD is that the fixed law doesn't apply anymore because there is turbulence. So we should use other workarounds, other formulations. In this case, simply is the fixed law for turbulent flows. Which solves the diffusion. So that's a parameter that's solved from the CFD solution. How it's done is a volume in volume, 2 volumes mixing together depending on their chemical characteristics. In our case, the chemical characteristics were the same because it was air and air. So it was simply the turbulence driving the mixing. that's all the physics that's involved in the simulation. Everything happens then after the dilution ratio is calculated. So the aerosol physics is modeled indirectly. So we know that when we breathe out, there is a percentage of the volume that comes out of the mouth that is occupied by droplets. We can't really measure the volume, so we measure the number of droplets. We know how big they are, so there is the volume of respiratory fluid that we calculated. So that's what we draw the parallel between respiratory fluid volume and the number of particles. So the evaporation is considered indirectly, let's say.
Thank you for the clarification, Giulio. And the last part of Majid's question is to do with the actual process of co-simulation. So he asks which CFD code was used and how was the boundary condition from the dynamic thermal model coupled with the CFD?
For the two works that you have seen, we use the Fluent. For current jobs that we are conducting that we will probably present at other occasions, we're using OpenFOAM. And the way the DTM informs the CFD is basically reading the surface temperatures and then setting them up in CFD. You don't need to set up a constant surface temperature. What you can do in CFD, you can also set up a heat flux, which is basically watts divided square meters. So it's quite immediate, I would say.
Okay. Thank you, Giulio.
You're welcome to email me if you need any information.
We will be sharing your emails if you allow us with the attendees if they have any other follow-up questions. I think the next question is particularly important and pertinent. This comes from Cherry Marquez, and she says, is this type of modelling useful for assessing the climate vulnerability of buildings and assessing thermal comfort? And by that, I think she means co-simulation in general. So, Esther, do you have any thoughts? Or Julia?
Yeah, so I'm obviously not an expert in modeling that, but I could imagine that it is useful as you can couple different tools and domain-specific tools with just other tools, and also include measured data or some type of data you have. Yeah, I think it should be possible.
And Julia, your thoughts on that?
There is actually quite a lot going on in terms of not really climate vulnerability, but thermal comfort. In terms of climate vulnerability, the official position of both the Met Office or the Wind Engineering Society is that we don't see different peaks in terms of the extreme action, extreme loads or extreme events to what was happening 50 years ago. They look in the media, they look more frequent, but actually what there is the media attention is simply a bit higher. So as such, we are not drawn into modifying our rules just yet because of climate change. What we want to do is having buildings that are better adaptive. So what Esther is doing is absolutely spot on, because we need to to have a building that is capable of changing its features to respond to the climate. In terms of the thermal effects, what we have in place in the UK is a requirement that currently only applies to some councils. The City of London, for it, is an example, where you need to calculate the thermal comfort in outdoor and indoor. There is a guidance available on the City of London website, and it requires modeling. So the CFD modeling of things is already well accepted by regulators, let's say. And there is in general a lot going on, because the public is becoming very pushy in terms of the things that we need to now consider when we design.
Yes, I agree. And that can only be a good thing when there's sort of a public driving force behind things. Our last question today is from Andrew Williamson, directed at Giulio. And he says, it would appear from your simulations that HVAC ventilation systems were not really performing as well as expected or required. The question is, have you analysed the layout of diffusers and grills to determine improvements and then to pass them on to industry and designers?
So this methodology has the caveat that the dilution ratio is basically steady. So if you multiply by a time, any position in the map in the graph seemingly becomes unsuitable. But actually, this is a very good system. Probably you were referring to the second test case. So for the first test case, the system is actually quite well performing. So when there is a bunch of people together, we can see that there is a low value. Single offices are single offices. So you simply, during the next pandemic, you shut them down or you request to open the window just for that room and they should solve things. In the second case, we pointed out that having a building which is partially ventilated is absolutely a no-go, especially if you are requiring people to work in there. But there is still the idea that the money is best spent somewhere. So if we need ventilation to absorb heat loading coming from ovens or the production activity, then yes, that's budgetable. If it is for making sure the workers are safe, that there isn't really any rules that prompts employer to do that. So if they can avoid to spend money, they would. So yeah.
Thank you very much, Julia, for that. We're coming to the end of our webinar today. I'd like to thank both of our presenters, Esther Borkowski and Julia Vita, for taking the time to share their work and their interesting findings with us. And as just as we've also posted in the chat, just as a reminder, please do join IBIPSA England if you're interested in hearing more about our events and activities in the area of building performance simulation. We've posted the link in the chat. It's www.ibipsa-england.org/join us. We would welcome your inquiries about membership and you becoming members of this organization. It can only get better with more people being involved. So please do join me in thanking our presenters, and we hope to see them and see you all in the near future. Thank you very much, Esther, and thank you very much, Julia.
Thank you.
Thank you.
Thank you.